So day 1 of the Polygon unit. We went over these a little bit first semester, so I'm not going to spend too much time. Polygon, the word, the parts of the word is a Greek word made up of poly and gon, where poly means many. It means more than 2. So poly is many, and gon actually means angle. So it's a shape with many angles, and therefore many sides as well. Here's some good examples of polygons in the real world. We've got some concave, we've got some convex, we've got regular, we've got irregular. So they show up a lot. I always try to convince you when we start a unit of where does this show up in the real world. So we've got stained glass, we've got quilts, we've got a fighting ring, we've got a Texas star, Texas pride, we've got a trampoline, we've got the Pentagon, we've got a washer, a picnic table, soccer ball, and road signs. So, yep, a star is a polygon. Yes, it is. Let's dissect the official definition of a polygon a little bit and talk about the most important words. Polygon. Closed plane figure with at least 3 sides that are segments. So the words that stand out to me are closed, plane, 3, and segments. Closed. First of all, it's a closed figure. All of the vertices connect. So there's none that, you don't leave it hanging. There's not one that doesn't connect to another, like this one, not closed. Plane. What does it mean for a figure to be a plane figure? P-L-A-N-E, not P-L-A-I-N. Flat. Okay, good, 2-dimensional. All right, so we've got 1D, 2D, 3D. At lunch yesterday, we had a conversation the teachers did about the 4th dimension, and we were researching it because we're really nerdy. But anyways, no, we'll only do 1D, 2D, 3D. A plane figure would be 2D, flat, 2-dimensional. Okay, we know it has to have more than 2 sides, which is the same as saying at least 3 sides. So the very smallest polygon possible is a triangle, very good. And the sides have to be segments. If the sides are not segments, it's still a shape, but it's not a polygon technically. So the sides do need to be segments. Okay, what I want you to do, you can fill in the blanks in your notes. We already talked about this last semester, so I'm not going to spend very long here. We've got convex, and we've got concave. Most of the shapes that you encounter or you study in math are usually convex. Concave is when the side has caved in. How you test if a shape is concave or convex, draw all of its diagonals. Overlapping, all that good stuff. If all of the diagonals fall inside the shape, then it is convex. If any of the diagonals, even one, lies outside the shape, then a side has caved in, and you call it concave. So it's kind of like, it's called a diagonal test. Like you have the vertical line test in Algebra 1. This is the diagonal test for polygons. All right, I want you to look at all of my choices here. A, B, C, D, E, F, G, H. And I want you to sort it as concave, convex, or not a polygon. If you're watching the recorded lesson, pause right here and try to sort it before we reveal. Okay, so it's not going to be a perfect representation. It's just kind of fun to take real-world objects and try to sort them. I don't know, Toby. I don't know. So let's start with A. This is definitely concave because we've got a side caved in right here. Additionally, if I were to draw the diagonal, which is a segment connecting a vertex to a vertex, it would lie outside the figure. B. Oh, I gave you 2 concave ones in a row. Any star, the outside of it, not if you draw the diagonals in the middle, but the outside of it is a concave polygon. If you take those individually, those are hexagons, concave polygon. If we take the floor plan and we're just looking at the outline, I don't know how you interpreted it, but if we were just looking at the outline of this floor plan, that would definitely go with concave, right? If you were looking at every object, it wouldn't really be a polygon. Regular, good old regular polygon in the yield sign. Nope. Nope. Oops, the G didn't go with it. And nope. So why is F not a polygon? Oh, I see. You're saying it wasn't a closed figure because of the doorways. Okay. We can put it here if you want. Not closed. Are the doors open or closed? Okay. Good. F is not a polygon because there's no segments, there's curves. What about G? Is a circle a polygon? Obviously no, a circle doesn't have any sides, and once again there's curves. And what about H? There's no curves there. Those are all segments. Ooh, it's 3D. It's not a plane figure, and it just looks weird. Okay, so 3D figures are shapes. They're figures, but they are not polygons. Once again, we already went over this, so quick review. Equilateral polygon. All sides congruent. Let's see if it's not disappearing. Equal angular polygon. All angles congruent. Just thinking. There we go. Oh, sound effects. So, equilateral, sides congruent. Equiangular, angles congruent. And then if it's both equilateral and equiangular, we call it a regular polygon. The most important word on this slide is regular. I'm going to use this for the whole unit, which by the way is a 4-day unit. Anyways, I'm going to use it all 4 days and talk about regular polygons. And when I say regular, I want you to picture lots of arcs and lots of tick marks. All sides congruent, all angles congruent. Lots of arcs and lots of tick marks. All responded. Good job. A regular polygon is concave. Always, sometimes, or never. What did y'all choose? Oh my goodness. So we've got about half sometimes and half never. So let's think about that. Regular means all sides are congruent and all angles are congruent. I agree with you that you can draw an equilateral shape that's concave. I agree, like a star. That would be equilateral, and I don't have a picture, and I'm not going to try to draw a really pretty one. But all of its sides would be congruent, but what about all of its angles? If you have an angle jutting in, like even if it had all sides congruent, which this one doesn't, I could force it to with my markings. What's the measure of this angle? Whoa. So that one is a never. It's a never. A regular polygon is never concave. Okay? Okay, that's enough vocab for one day. Let's go to that table, because I know you love to just fill in tables and you don't want to leave anything blank. So I don't focus on the picture right now. I do just want to focus on the words, and I want to focus on finding a pattern with the angles. For the rest of the class, we're focused on angles. No more vocab, no more technicalities, just the numbers, the angles. Let's fill in the first row. Triangle. This, you probably have no idea what that means, but a triangle has one triangle, by the way. What are the sum of the interior angles? You already know that. If it's regular, that's what this asterisk means. If it's regular, then what's the degree of one of its interior angles? Good. It's called an equilateral triangle, and its measure is 60. We're going to save this part for in a minute. Okay, 4 sides. That's called a quadrilateral. You can draw any quadrilateral you feel like. Now I want to explain what it says when it means the number of triangles. So if you were to draw the diagonals of the shape, but not all of them, if you were to split the shape into triangles by drawing the diagonals to where none of the triangles can overlap, so if I drew a diagonal here, I would have 1, 2 triangles. I could split a quadrilateral into 2 triangles. Doesn't count if the triangles overlap, so be careful. Each triangle has 180 degrees. So 2 times 180 is, so a quadrilateral we already knew had 360 degrees. What is a regular quadrilateral called? A square. And what are the angles of a square? How many degrees? Okay, so those 2 were easy. Now let's do, I'm going to just show you the rest of them because I don't want to take time you watching me write these words out. Let's talk about a pentagon. I'm going to go to a little bit larger of a screen so that I can talk about this with you. Maybe, frozen. Okay, so I'm going to cheat too. I'm going to draw a pentagon. It's automatically regular, but we don't really care about that. So, oh, I drew 2. Oh, it's like a little baby pentagon. We don't need you. Okay, so I'm going to pick one vertex, a single vertex, and I'm going to draw every diagonal that exists from that vertex. So this is not a diagonal. That's a side. So here's a diagonal, diagonal. Oh, that's just a side. Okay, that's not a diagonal. How many triangles did I create? How many degrees does each triangle have? So, what is the sum of the angles of a pentagon? There we go. We got pentagon. I was able to draw 3 triangles, 540 degrees. Now, if it's regular and all the angles are equal, what is the measure of one interior angle? You got it, Sharon? Good, Hatham. Good connection. Yep. Okay. Let's stop right there because someone already wanted to make a connection. What's going on with this column? Just what's happening? What do you notice? Each time it's going up by 1. Yes. Okay. What's happening in this column? Each time it's increasing by how much? 180 plus 180 plus 180 plus 180. What's happening in this column as in, just go with for now, increasing or decreasing? Good, Alex. Okay, what? Yes, increasing. As our shape increases the number of sides, the angles get larger and larger. What number are they approaching? What's the largest an angle could be in a polygon? Random answer. The degree of an angle. There we go, Desalin. 180 would be the limit. Can't even get to 180. Can't be a straight line. So those numbers are going to approach, it's called a limit, but we won't talk about that here, approach 180. Thank you. Good. What about convex? So we're really, all of this is applying to concave. I'm glad you said that. It's applying to concave. Okay, so now I want you to, you can fill out the rest of your table, and I'm not going to bore you by filling it out in class, okay? But what I want you to do is make a connection now, and a student already did it, between these two numbers. We're going to call the number of sides n for the whole unit. Anytime I say n, I mean the number of sides. N, number of sides. Same with the number of angles. They're the same. Like an n-gon, yeah. Okay, so n is the number of sides. How does the number of sides relate to how many triangles you can draw? Okay, so there's always 2 less triangles than the number of sides. So the number of triangles you can draw is n minus 2. So if I had a 50-gon, how many triangles could I draw? I could draw 48 by drawing the diagonals. Okay, now what do we do with this column? Am I drawing enough arrows to get to this column? What did we do to that number? Multiplied by 180. Good. So to create this column, we've got n minus 2 times 180. That's a formula. That's a formula, and we could use it for an octagon, a dodecagon, a 50-gon, a 100-gon, a 20-gon. No matter how many sides we have, we can use that formula, and we don't need to memorize a table. You know what I mean? Okay, how do we get from this column to this column? We took the sum of our interior angles and we divided by the number of sides. Not by 3 every time, but the number of sides. Good. So n minus 2 times 180 divided by n. And I have those all pretty on a slide that you can add to your notes, except I added some extra slides. There we go. You can squeeze these on the front of your notes, or if you don't have room, feel free to add them to the back of your notes since it's empty. You perfected the formula. So to find the sum of the interior angles, take the number of sides, subtract 2, remember that's the number of triangles, and then multiply it times 180. To find just one interior angle, only if it's regular, then you take that same sum and you just divide it by n. N stands for the number of sides. That's a good point. The number 7 in your table, the numbers are ugly. They're decimals that do not repeat. So please write it as a fraction. Do not round the sum of the interior angles, or sorry, one interior angle. Do not round, please. Okay, now let's talk about the exterior angles, because we left those columns blank. So the orange ones, X, Y, and Z, those are interior angles. We're used to that. Now, if you extend the sides, they don't exist if you don't extend the sides. I mean, they exist, but you can't see them. If you extend the sides, and you can do it to all of them, not just 3 of them, then you create what's called exterior angles. X, Y, and Z, the pink ones, are the exterior angles. Now, before we decide how many degrees are in the exterior of a shape, I do want to talk about real quick, what is the relationship? I shouldn't have called them Y and Y, so pretend those are different numbers. What are different letters? What's the relationship between an interior angle and its exterior angles? Good. What's the vocab word that has 2 words to it? There you go, linear pair, yes. So an interior angle is always a linear pair, forms a linear pair with its exterior angle when you extend the side. Okay, let's pull Geometry Sketchpad up, and let's see if we can investigate the sum of the exterior angles. All right, so what shape do we have here in Geometry Sketchpad? We have a good old pentagon, yes, pentagon. Now, the cool thing is the number of degrees inside is not really going to have any bearing on the number of degrees outside, and we're going to see why in a moment. So, right now it's a regular pentagon. You can't really see, but all of the angles, oh, well, let me draw it. All of the angles are 72. So, I don't want to see if it works on a regular one. I want to make sure whatever conclusion we're going to come to, I want to make sure it can work on any pentagon. So what we're going to do is we're going to shrink the pentagon, and take a look at what happened. What shape was formed when you put all of those angles adjacent to each other? A circle. And how many degrees are in a circle? 360. Show the sum. They all add up to, can you all see that? Not very well. They add up to 360. Okay, so let's stretch that back out. So that's what the angles, the exterior angles add up to for a pentagon. They add up to 360. Now let's do one less side. Let's do a quadrilateral. It's not a square, it's just an irregular quadrilateral. So let's see what they add up to this time. Dun, da, da, da. Oh my goodness, shocking. Same result. Show sum, even though they're all different, and even though angle 5 is 0 degrees because it's a quadrilateral now, it still adds up to 360. Hide sum, stretch back out. We'll do one less side again. Let's do a triangle. Shrink. So now each angle is larger, those angles are bigger, but when you juxtapose them, when you make them adjacent to each other, once again, it makes a circle. That works for concave and it works for convex. So, moral of the story, right? Maybe. What is the sum of the exterior angles? What is it? 360. All the time, every time, go to that column and write it all the way down the column. 360, 360. Oh my goodness, that's so cool. We don't have to memorize another formula. No matter what the shape is, whether it has 3 sides or 1,000 sides, can it have 1,000 sides? Anyways, whether it has 3 sides or 1,000 sides, the sum of its exterior angles are 360. So, the sum of the exterior angles, there's no formula for this, it's a constant. The sum of the exterior angles is 360. And if we had a regular polygon and we wanted just one, there you go, just one exterior angle, what its formula would be, write it down, 360 divided by n, where n stands for the number of sides and therefore the number of angles. 360 divided by n. Okay, let's put these formulas to use. So you have 4 formulas. You are not going to be given these on the quizzes and the assessment, so just make sure, really you only have to memorize two things. If you can memorize the sum of the interior and you can memorize the exterior, to create these two, you just divide by n, divide by n. So you really only have to memorize two things. Memorize sum of interior and memorize sum of exterior. Let's try some problems. Find the sum of the measures of the angles of a 30gon. I need to go over this. I know you can plug numbers into a formula. So this is our n right here. It doesn't really have a name. When they don't have a name, or I'm not going to make you memorize its name, then you just write the number and then you write gon. It's like 30 gon, 52 gon, 79 gon. So that is your n minus 2 times 180. I don't want you to start using this formula like crazy and forget where it came from. Don't forget where you came from. What is the 30 minus 2? What does that even represent? That is how many triangles you can divide a 30gon into. So I can divide a 30gon into 28 non-overlapping triangles, and each, when you hear each, you multiply. Each one of those triangles has 180 degrees. Let's try. If the sum of the measures of the angles of a polygon is given, how many sides does it have? So this one's a work backwards one. I'm giving you the sum. Yeah, that's a lot of degrees. And you tell me how many sides it has. Okay, I see a little bit of variation here, and I want to talk about that because that's a common mistake. So I'm glad you did that. So we know our formula is n minus 2 times 180, and that is equivalent to the sum of the angles. Now, order of operations says we have to divide by 180 first to solve. We get n minus 2 equals 34. When you're solving for a variable, you do the opposite of what's being done to it. So be careful. The opposite of minus 2 is plus 2. And the answer to the problem is, that is a 36 gon. So a lot of answers I see that are wrong on the quiz are 32 and 34. You forget to add the 2, so be careful on that one. Okay, next question. A regular polygon is given. Oh, we just talked about that polygon. What is the measure of one of its interior angles? What is the measure of one of its interior angles? We're just trying these formulas out. We're trying them on for size, seeing how they work. Okay, how do we do? Ooh, we got a few different answers there. Okay, people are changing it now. Okay, so be careful. So, I bolded these, but on a quiz or a test, they're not going to be bolded for you. You need to look for keywords. First of all, it's regular. That's good. So we can use our formulas that have a star by them. And I only want one. What's the measure of one angle? Remember, the biggest we're allowed to go is 180. So don't ever put an answer that's larger than 180. That wouldn't make sense. So we do n minus 2 times 180 divided by n. The only way you could mess that up is by entering it into your calculator incorrectly. So make sure you use parentheses, and then you can just press enter after you do this, the numerator, and then just divide by 36. Okay? So the answer to that one was 170. Let's try and have a couple more for you. The measure of one interior angle of a regular polygon is given, so I'm giving you the one interior angle. It's regular. What is the name of the polygon? So here's the long way to do this. Some of you are really good at algebra. You might like this way better. You take the formula for one interior, and you set it equal to the angle you're given. And you solve for n. It's kind of hard to solve for n, and there's multiple algebra steps. So what I want you to do is be savvy. If this angle is 172.8, what is its corresponding, well not corresponding, what is its linear pair? What is its exterior angle? If you can find its exterior angle, it's tiny, it's weird. If you can find its exterior angle, then you can use this formula. And oh my goodness, if I had to pick A or B, I would pick B every time, right? But you had to know the trick. You had to know to find the linear pair of the interior angle. You have to remember the trick when you get stuck and you get that ugly thing. So you can put this over 1 and you can cross multiply. 360 times 1 equals 7.2 times n. And then divide to get rid of the coefficient of n. How many sides did it have? You looked up the name, but yes, 50 gone. It ended up having 50 sides. You don't have to memorize the name of that, so you can just call it a 50 gone. Okay. Real quick, what's the measure of the sum of the exterior angles of a nonagon? And everyone answers 360. The measure of 1, we just did this. I'm giving you 1 exterior angle. What's the name of the polygon? So no converting necessary this time. You take the formula for 1 exterior. You set it equal to your answer. If you want to just do 360 divided by 9, that's cool. But if you want to show this step, that's okay too. Divide by 9. Divide by 9. What do you get? A 40gon, a tetracontagon. Okay.